Welcome everyone to the 2022 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from John Atkinson, the Principal Product Engineer at Chroma Technology. John has over 20 years of experience as an engineer and holds a Master of Science degree in Photonics. Today he will discuss multispectral imaging in the SWIR with optical filters. If you have any questions or comments, you can type them into the conference chat box, which is right on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. You can also ask questions later on if you would prefer. If you have any technical issues during the event, please log out and log back in to rejoin. Lastly, John, we appreciate you for taking the time to present here at the 2022 Vision Spectra Conference.
Okay. And you can see what you need to see.
Perfect.
All right. Hi. Yeah, I'm John Atkinson. I work at Chroma Technology Corporation, an employee-owned company making the world's finest optical filters right here in the great state of Vermont. I'm going to talk to you today about multispectral imaging and the SWIR with optical filters. Just so you know, Chroma Technology has been around for over 30 years, and we've been making optical filters for life science, astronomy, and industrial applications ever since. So I'm going to start with a little introduction, introduce shortwave infrared, SWIR for short, what that is. I'm going to go through some optical filter basics. Then I'm going to discuss briefly the different ways one could do multispectral imaging. And then we'll discuss choosing the right optical filters for your multispectral imaging application. And finally, I have a few examples to show. So everything that has a color has some kind of spectral signature. This apple, for example, is reflecting red light, and that's what you can see. When light interacts with any object, it's either reflecting, absorbing, transmitting, or in some cases, re-emitting incident light. For example, we make optical filters for fluorescence microscopy, and in that case, the objects are actually taking in some of that energy and then re-emitting it at a different wavelength. The amount of reflection, absorption, etc. varies with the wavelength, and this variation depends on the wavelengths that make up the light that is incident upon the object, and of course, the nature of the object itself. Some objects, like, again, this apple, are reflecting red wavelengths from the sun's visible rays and absorbing the rest. We see the apple as red, but you might want to ask the question, what color is it really? We perceive it as red because our eyes can see red light, and the reflecting spectrum of the apple is heavily weighted toward the red. In fact, the apple is reflecting other wavelengths of light beyond the red into the infrared, but our eyes are not able to see this IR light. Some objects have kind of a boring reflecting spectrum in the visible wavelengths, and there could be other interesting, more interesting spectral signatures in the near IR or shortwave infrared or SWIR. In this plot, going along the x-axis, you can see visible wavelengths of light from about 400 to 750 nanometers. There's some reflectance spectra of dry grass, regular grass, and some trees. And there's interesting things going on in the SWIR up near the 1,000 to 2,000 nanometer range. There's some dips and absorption where water absorbs around 1450 and 1900 nanometers. You can see the wet grass or the green grass has a absorption peak in those places, but the dry grass does not. One can exploit that fact and use those bands of light or those colors of light to tell the difference between these two objects and many other things. Back to our fruit, you can see that apple in the SWIR range or near IR to SWIR range has this reflectance spectra. And it's similar to these other fruits, orange, nectarine, and pear, but at certain places there's definitely a differentiation between the four. For example, around 1200, you can see there's a reflectance difference. And again, in that band, one could image and tell the difference between these two, these four objects. So again, the SWIR range is just one chunk of the electromagnetic spectrum within the infrared. To the blue side, we have the near IR and then visible light, which is what our eyes can detect. Beyond that, on the blue side, is ultraviolet light or even X-rays. To the red side, certainly the infrared is beyond what our eyes can see and goes all the way up to microwaves and eventually radio waves. So the SWIR range I'm defining is basically between 1 and 3 microns. This roughly corresponds to the spectral response of the semiconductor indium gallium arsenide. This plot here is showing typical responsivity curves for a silicon detector that covers the visible quite well, peaks around 1,000 nanometers or so in the near IR, but then drops off past about 1,100 nanometers. This typical in-gas curve has responsivity around that crossover up to 1,700, but there are in-gas detectors with extended range. There's also colloidal quantum dot technology that has this whole range combined. There are cameras made with those sorts of detectors. Because most objects reflect some amount of the SWIR light as opposed to absorbing it, it can be a really useful range for a variety of applications. So here you can see the plastic bottles in the visible. Some of them are transparent, some of them are in fact opaque with visible light, but you can see through them with SWIR light. And because the water or the liquids inside these bottles are absorbing the SWIR light at varying levels, you can tell where the fill level is. The middle set of images, there's smoke in front of this building, which makes it hard to see in the visible, but the SWIR can see right through the smoke. That smoke is transparent in the SWIR wavelengths. The SWIR wavelengths reflect off the building and then back to your camera so that you can see it. The set of images on the right, this is coffee beans with a couple rocks mixed in. And here in the SWIR, you can see the rocks are absorbing more of that light, whereas the coffee beans are not. They're reflecting that light. So you can see a good contrast between those two types of objects. And here, the apples in the color and monochrome in visible light, there's no bruise that can be discerned. And yet in the SWIR, clearly you can see a bruise. So there's definitely applications for SWIR where you can see things that you cannot see in the visible. There's lots of remote sensing applications which I'll dig into too, having to do with crop health, etc. Many other applications for SWIR lighting and SWIR imaging include agricultural monitoring, I already mentioned, waste management, recycling, even art inspection. The SWIR light goes through certain pigments. Semiconductor inspection, for example, solar cells, food inspection, thermal imaging, and life science, to name a few more. So what are the basics of optical filters? An optical filter is essentially a device that transmits or allows some wavelengths to pass through it and rejects or blocks other wavelengths of light outside of that pass band. They can be used in imaging devices to highlight the interesting spectral signatures, increase the contrast, and get rid of the noise. So you're getting more light you want and projecting light you don't want. This plot here on the right is showing a transmission curve of that filter, and it's cutting on around 580, cutting off 625 or something. So it's allowing those wavelengths of light to pass through, and it's essentially zero transmission or blocking outside of that band. Most basic image systems have a filter. Here in this little cartoon here, the filter happens to be outside the lens, but it could in fact be between the sensor and the lens, depending on the situation. This is just a basic setup with sunlight and an apple, but this light source could of course be a bank of LEDs, and the object could be lots of other things. So now I wanted to discuss multispectral imaging. What is it? Essentially, it's capturing multiple images. Each image is captured over a particular band, a spectral band or color. In an RGB camera, there are three channels, red, green, blue, three color channels that are collected. In a multispectral, there's usually more than three, so several discrete bands. I'm showing, I think, 8 here or so. Hyperspectral is essentially it's the same thing, but now it's a continuous spectrum. So you have all the points in between are filled in. And again, with any of these techniques, you're gaining more information than what could otherwise be obtained with just the black and white image. So that gives you spatial information, and this allows you to get spectral and spatial information, which can tell you a whole lot about whatever it is you're looking at. There are a variety of techniques. Depending on the application, one might be better than another. Some of these techniques involve more complicated optics, dispersive elements, prisms, more complicated paths for the light to go. The technique that uses a passive component like the optical filter are often the simplest and cheapest solution. Here's a few of the approaches, multispectral approaches that use filters. In one case, you could have multiple cameras, each one with its own filter. You could have a camera with a multi-band filter. So that's a filter that transmits more than one band. It transmits, for example, 4 bands if it's a quad band filter. Another technique would be to use a filter wheel in front of a camera. Of course, the less cameras may be the better for certain applications, although a low-cost camera with each with its own filter could be the best way to go. For example, in remote sensing applications, using optical filters in this simple way really operationalizes imaging for precision agriculture. Flying just a handful of cameras with each with its own filter, as opposed to a heavier, more expensive hyperspectral camera, could be the way to go. For machine vision or industrial applications, there's advantages to using optical filters, not just to increase the contrast in general, but as opposed to other multispectral solutions, it's a much simpler system, can be much lower cost. The filters can be customized for exactly the situation, the pass-fail criteria. And by that I mean the filter band can be narrower or wider and placed precisely where it's needed in order to differentiate between two different objects, for example. The filters allow for spectral separations, so crosstalk, the noise, essentially, the ambient lighting, all of that can be rejected so that you're only passing through the signal that you want and not the noise. This allows inspection lines or robots to move a lot faster, and the overall inspection could be a lot cheaper. For the multiband filter, there are applications where if you have multiple LEDs turning on and off sequentially or strobing, you could save a lot of money on an expensive camera. You wouldn't need a filter wheel and can potentially discern a lot of information that way. So choosing the right filter, as I said, the filters can be customized to place a band or a pass band anywhere you would need it. This plot here on the right is showing the reflectance spectra, again, of green grass versus dry grass. The dotted blue lines are the center wavelengths of the bands from the Sentinel-2A satellite multispectral camera. And you can see there's a pretty big gap between about 945 and 1375, where there's no spectral information to be gained. This group, a group of scientists came up with this other set of bands to sort of fill that gap. And you can see that they line up with some features in the green grass, right? So the whole point is to differentiate between these two reflectance curves without having to get the full spectrum. So these bands here, for example, might be of interest. The 1620 nanometer band shows a pretty good separation between green grass and dry grass. There's an even better one if you put a narrow band right around the water absorption line, 1450 nanometers, you can get a larger contrast between the two. So this sort of information can get used to differentiate between grass that needs water or any crop that needs water. You can also discern the biomass itself of the plant matter, the nitrogen content, the chlorophyll absorption, and all of this tells a farmer what plants may or may not need attention. You might need some fertilizer here, but not there. You might need some water in one field and not another field. And this is really sort of driving enabling the smart farming that needs to happen to sort of more efficiently produce food in the world. In an industrial application, the filters here are lined up pretty closely with the peaks of these SWIR LEDs. You can see the LEDs overlap quite a bit. And the filters, what they do here is they're going to block out all those in-between zones, right? And just pass the strong SWIR LED signal without incorporating the noise, essentially. Filters that are made with sputter dielectric interference coatings on just regular optical glass have the highest level of spectral performance and the durability needed to deal with extreme conditions. For example, even space, high altitude, or factory settings where it could get hot or cold. The dielectric filter transmission spectra here in the red is showing a very steep slope. It's a fairly narrow band, but it's capturing just the peak of the SWIR LED shown here and rejecting all the rest. The color glass filter shown, which is commercially available, has lower transmission, much broader band, and it's a lazier slope, not to mention all the red side SWIR leakage. So the dielectric filters that are sputtered can be customized too for any wavelength, any center wavelength or bandwidth. So we could move this to the red, to the blue, wherever necessary. So I got a couple examples I already sort of touched on. In this machine vision example, we have a SWIR camera and a multiband filter. So that's allowing these 4 bands shown in the top right to pass into the camera at nearly 100% transmission. The multiple LEDs can be strobed, so one at a time, and the imaging is taken for each light, and this can all be done very, very quickly. So the idea here is not necessarily just to see the bruises on the pairs, but you could discern other pieces of information. For example, is there wax on the pair? What is the wax on the pair? And a robot could come along and poke off the bad ones, the ones that don't meet the pass criteria. The multiple bands give you more information than just a single band, and there's no filter wheel, so all of this could be done pretty quickly and speed up the line. I already touched upon the remote sensing example. This little cartoon here is a drone carrying 4 cameras, each with their own filter. Again, this is a much cheaper and lighter package than a hyperspectral camera. The UAV can fly around. If it crashes or there's an accident, you're not losing your very expensive hyperspectral camera. So again, this is moving toward operationalizing precision agriculture. It's a much simpler approach, so you can fly more times, and there's a whole lot less data to crunch, because essentially this will give you just the images you need to get the information that you want, right? Does it need enough? Does it have enough nitrogen? Fertilizer? Does it need to be watered? What's the biomass? How big are, how much plant matter is there, right? And filters can be customized, of course, to highlight any key absorption feature. Again, biomass, nitrogen are just a few of the things that researchers are out there finding out just how much information can be gained from the SWIR wavelengths, combined with visible wavelengths. These new indices that are being devised in one drone flight can give you much more information, higher contrast images, and really allow for more precision farming. And that is my talk. Again, thanks for joining. And I think now I could take a few questions.
John, thank you so much for presenting your research on multispectral imaging and optical filters. We do have time for a couple questions, and with that in mind, I would like to remind everyone in the audience, if you haven't already, you can type your questions, you can type your comments into the chat box that is on your screen, and if they have not been answered, you will be reached via email at a later date. So John, what applications can maximize the benefits of a sputtered filter, would you say the most?
Well, the sputtered filter, any situation where you have a extreme environment, especially humidity, you're going to want a sputtered filter. The other kind of filter technologies will degrade if they get wet, if they get too hot. So certainly applications in space or in high altitude. The other thing sputtering allows is the spectral precision. So the deposition process itself is very repeatable. It's a constant rate of deposition, which allows you to lay down a coating of a very precise thickness, and that translates to very precise spectral band. So you could make a narrow band filter or a wide band filter and have the center wavelength or the cut on and cut off be exactly where you need it. So yeah, that's really what sputtering allows for.
Awesome, thank you for that. Are there situations that require both visible and SWIR filters?
Yeah, I touched upon that a little bit with the remote sensing application. There are traditional vegetation indices that use visible and near IR channels. Some of the spectral signatures of plants, with or without nitrogen content, for example, or water content, there's a lot more contrast if you go into the SWIR. So imagine a situation where you have images stacked up that are not showing a lot of differentiation because there's just not enough of a signature in that spectra, right? In the case of the SWIR, sorry, I was trying to get up to this slide here. You know, you can see here like a very strong water band and a lot more features to kind of hone in on, right? So you want to put those spectral bands in places where there's more differentiation, and that might be the SWIR for a lot of things.
Awesome, thank you for that. I got one more question for you here, and do
Sure.
filters allow you to ignore ambient light?
Possibly, yes, because if the filter is designed appropriately, it will block out all the unwanted light. So ambient light, to the extent that it is noise, should be blocked out. So if it's an industrial setting, there could be a factory where there's some lighting or windows open or other things going on, and that light could contribute to the noise, and the filter would need to be sort of customized to take care of all that. In the case of remote sensing, you have a lot of ambient light and sunlight, so really there you're just trying to squeeze down the spectral bands of interest and get rid of the rest. So certainly ambient light has to be taken into account when considering
Awesome,
all.
thank you for that.
Yeah.
I'd like to remind everyone one last time, if your questions haven't been answered, you will be reached via email. And this session is hosted by us at Photonics Media, and we certainly hope that everyone is enjoying the 2022 Vision Spectra Conference. John Atkinson, thank you one last time for presenting multispectral imaging in the SWIR with optical filters.
You're very welcome. Thanks, Jake.